We'll proceed in curl in calculus and then Stokes theorem. Very, very, very powerful. Okay, so we will proceed in curl and we will see Stokes theorem. But before we talk about the Stokes theorem, let's do some hands-on exercises. What we have learned. If I have a if I have a vector field, every time I start with the vector field because vector field is playing role out here as vector field is different from vector where vectors each component is numeric, then it is called vector, and vectors each component is algebraic, then it is called vector field. Now if I have a vector field and I want to calculate line integral of the vector field along a line, then it is called line integral. If I have a vector field capital F on the top, write one arrow mark. This is sign of a vector. Vector field, if I have a vector field and I want to calculate its integral along a line, these are very hi-fi terms, right? What is integral along a line? Tell me, any mathematics student, he understand this concept. The line integral of a vector field line integral. Does anyone really understand this? So I will initiate this and then kind of we'll move. That's why we are here. People have made the mathematics so complex and they use so hi-fi terms that no one can understand. Okay? So we will understand something that is very simple. Mathematics is the simplest thing in the world. But if you understand step by step, otherwise, beyond a level, beyond a numeric level, you cannot enter into algebra. Okay. Now, as I say that 99% of the mathematics is numerical science. 1% is algebra, vector, field, vector, calculus, different coordinate system. If you are not powerful in numerical science, you can never proceed further. Straightforward. Now, if I say that, like the example I give, that if I have a surface, if I have a surface, if I have a surface and I have an item, okay. Now, consider there is some load is there. There is some load and someone is pulling, this is a load, that this is earth. This is earth. If this is earth and then someone is trying to pull this load on the earth, okay, so he pushed he pushed this item 2 meter. He pushed this item 2 meter and he applied 2 unit of force or 5 unit of force. I believe the unit of force is Newton. I don't know. Consider it is Newton. So 5 Newton of force he applied. Through that it moved 2 meters. Then what is the work done by that person? If if on earth some load is there, some weight is there, and I am pushing it, okay, and from my body I am applying 5 Newton of force, okay, and then it is moving 2 meters. How much work I did? 5 into 2, force into displacement is the work done I did. 10 joule of work I did. Okay. Now consider that rather than, now how I am pushing it, the workload, the work is there and I am pushing exactly in the direction of the where it is moving. So my push is exactly in parallel to the earth. Now I am lazy. I am lazy and workload is there and now I am standing, rather than coming, sitting and then pushing it so that it will be parallel to the earth. Now I am standing and then pushing it. It is something like, now I am standing and trying to push like this. Okay. Now I am applying 5 Newton of force. Same force. 5 Newton of force. Okay. Will the work done will be same? Or if work done is 10 joule and it moved 2 meter, am I really applying 5 Newton of force? That is under question. So earlier I applied 5 Newton of force along the movement, 5 Newton force, and it moved 2 meter. So 10 joule work done. Consider now I am applying force like this, where it is making theta angle with the earth, and then it moved 2 meter. Okay, if it moved 2 meter, or consider that net work done on this item is 10 joule. Net work done in this item is 10 joule. How much force I am applying? If I apply 5 Newton of force when angle is 45 degree, will it move 2 meter? If it moves 2 meter, then it will be slow now. If it moves 2 meter, will it be 10 joule of the work that is done? Many questions are there. If 10 joule of work is done, then what is the force I have applied? If I have applied 5 Newton of force with, with angle 45 degree, then how many unit it would, how 5 Newton of force and it moved 2 unit, 2 meter, then how much work is done? If work done is 10 joule, then and force is applied at 45 degree, 2 meter is moved, then how much force is applied? All are circulating around the same thing. Now the effective force, if force is like this, then effective force is F cos theta. Cos 45 degree is 1 by square root of 2. I believe I know this much. So 1 by square root of 2. So force into 1 by square root of 2. I believe a square root of 2 is 1.414. So force got divided by 1.414. So force is reduced now. If force is reduced and if it moves 2 meter, then suddenly it is not doing 10 joule of work. If it is doing 10 joule of work, then 10 equal to 2 into F cos theta. F cos theta equal to 5. Then force equal to 5 by cos theta. Cos theta is 1 by square root of 245 degree. Then the force applied is 5 into square 1.414. Okay, then it will be around, I believe, 7. If someone applies 7 Newton of force at 45 degree and then it moves 2 meter, then he has done 10 joule of work. Can you see this? A lazy person has to work more, has to apply more force to get same work done. Now I am very lazy. Now I am applying force like this, 90 degree. Will it move? It will not move. Means very lazy person cannot do any work at all. But if I applied force at 80 degree, and then it did 10, it moved 2 meter, then how much work it done? Okay, then force cos theta, okay, force into cos theta into 2 meter. That is the work done. If force is 5 Newton, then cos 80 degree, then it will be near to 0 only. I believe, consider it is 0.1, then 0.5 into 2, then 0.5 into 2, then 1 joule of work done. If force is 5 and it moved 2, then work done is 10 joule. If force is 5 and angle is 80 degree, and if cos 80 degree is 0.1, then work done is 1 joule. So as we are moving, if force vector is along the displacement, then full force is applied on the load. But if force is growing in the angle, then net force will be F cos theta. That is very less, and that much is applied. So net work done will be lower if the angle is increasing. What is the consider this displacement is happening on x-axis. Consider this displacement is happening on x-axis. If displacement is happening on x-axis and this is the force, then how much is the force then? I don't bother about now. Vector is coming into the picture because force is now has direction, now it is changing its direction. If that is the case, then displacement is not far behind. It is also saying I have some direction. So displacement is along x-axis. So it has direction of I vector, unit vector. Whereas force has a vector now, capital F. So capital F dot direction unit vector. If direction is not unit vector, then if it moves 2 units, then it is 2I vector. 2I vector. So capital F force, that is vector now. So dot product means, now we are going to do dot product. Dot product of two vector, if capital F dot I, F vector dot I say, then that is nothing but F cos theta. What is this vector's magnitude or essence or its presence along the I vector side? If it is F and angle is theta, then F cos theta into the displacement. This is what we are saying. It is same as vector F dot I unit vector, that is F cos theta. What is F uh, F essence? Okay, F presence. F, you can say like if there is a force, vector field, then what is its effect along the x-axis? F dot I vector, that is dot product. So F cos theta. So rather than saying cos theta, now and this I have moved 2 unit, now it is 2 into magnitude into the unit vector, that is 2I. So vector capital F dot 2I is the work done. If vector capital F that is like this, so how I can deduce a vector in this way? So if it is origin, then let's take it to origin and see what is the vector. So it will be like this is positive, this is negative, then this is negative and this is positive, then vector field or like this, then like this, then this is positive, this is negative, then I can say something like I minus j. I minus j is a force field where its power is 1 square plus 1 square, 1 square plus minus 1 square, a square root of 2. That is the power of the vector. So I minus j is the direction of the vector, or I minus j divided by square root of 2 is actual unit vector, whatever it is. Now, what is the work done by a vector I minus j along 2I? Then I dot 2I, I dot 2 I minus j dot 2I. So j component gone, and now it is work done is 2. Work done is 2. If the force is a square root of 2 Newton, then means I minus j means it is making 45 degree. If force is a square root of 2 Newton, then a square root of 2 cos theta, 45 degree. 1 by square root of 2 into square root of 2 gone. Then net effect along the x-axis is 1 Newton only. And if it moves 2 meter, then it is 2 joule of work it did. But if it had applied a square root of 2 unit of energy along the x-axis only, then work done was square root of 2 into 2 joule of the work. But in vector notation, if force is making 45 degree, then it is I minus j when the magnitude of the force is square root of 2. Then I minus j dot 2I is 2. That is the work done. Or I minus j, the magnitude of the force is square root of 2 cos theta means 1. 1 into 2. So now consider that this I minus j is a vector. So what is the work done by a vector along a displacement is vector field dot displacement vector. Vector means force vector dot displacement vector. If I do dot product, it will give me the net work done. Now force vector is a algebraic vector. Instead of I minus j, it is x plus I minus x plus sin yj. Vector is changing. If I move along x-axis, this vector was earlier like this, it is changing everywhere. That is called vector field. And the line I had taken was x-axis. It is again changing like circular path if I take. From one point to another point, if it is moving, instead of a straight line, I am taking a circular path. From here, it is taking a circular path and going to B rather than a straight line. Everything is vector field. Now, displacement is a vector field. Earlier, it was a static vector. Force was a static vector. Now, it is a vector field, algebraic vector. If it is both are algebraic vector, then what is the work done? Same thing. Capital F dot R vector. Capital F dot R vector. But directly we cannot multiply. Earlier we were multiplying directly when it was numeric. But now if I multiply directly, then it will not happen. Okay? Because we need to calculate area. If I want the multiplication of two algebraic equation where both are varying, then it will tend to, then multiplication will be transformed into area, integral calculus. Please watch the video of integral calculus. So now it will land up in calculating the area to get the multiplication. So multiplication of vector field capital F dot R vector, both are vector field, then we cannot multiply directly. Okay, how you can multiply directly? Not possible. So you have to now go with the finding the area. Okay, finding the area to have the net computation. Finding the area to have the net computation is nothing but integral calculus. Now R vector will change into dr vector, and whole term is called line integral of a vector field, where from it started and we land up where. So line integral of a vector field, that is capital F vector dot dr vector, that will give you the exact. Now if this is a force field, and this is a displacement field from here it is going like this. If this is the displacement field, now this item is moving in a circular path from here to here, and this is force field which will keep changing everywhere. Displacement is also keep changing everywhere. If that is the case, then what is the net work done? Moving this mass, because of this force field, this mass is moving like this, and force field is varying also here to there, then what is the net work done? That is force field dot dr vector, where r is line vector, that is circular here. Force is vector field. Integration from A to B. Now it has come to this stage, and it is called line integral of the vector field. Line integral of the vector field is nothing but simple multiplication of a vector capital F dot along the line. But with line is algebraic and force is algebraic, now it will come to integration. So capital F dot dr vector means capital F's line integral along the r vector from point A to B. If capital F, that is a vector field, if it is force field, then it is work done. Otherwise, it is line integral. So line integral of a vector field along a path from point A to B is called line integral of the vector field and line integral of the vector field. If this vector field is force field, then it will become work done. Okay, here people start with, now let's calculate the vector field line. 100% of the students, their vector field is in sky. Okay, now they are playing game in their mind. What they will understand when they enter the classroom and directly someone is talking about vector field line integration. So this is the concept behind the scene. So before we into the Stokes theorem, let's do some practice. What we have learned? We have learned that line integral of a vector field in a closed loop. I talked about A to B. If it is A to A, means it takes a path and then come back to A. If it is A to A or in a closed loop, line integral of a vector field, if it is 0, line integral of the vector field, it is 0, then it is considered as path independent. But A to B, for all possible paths, this is one path I am saying circular, another path can be a line, A to B, B to A, another can be rectangle, A to B, B to C, C to D, another can be parabolic. If you take all infinite path, if you take all infinite path from A to A to A, all infinite path, so many paths, and everywhere line integral is 0, then it is called path independent. First, tell me one person who can try 2 or 3. I'm not talking about infinite. Will he able to sleep in the night? Not possible. So then people found out that if I do line integral of vector field capital F dot dr vector along the line or curve r vector field, so this dot product will bring you one algebraic equation. If you do, I'm not talking about limit. If you do integration of this, it will land up in another algebraic equation, that is small f. It is also called potential function. If there is a small f, that is a potential function, for which if I calculate gradient vector, for every algebraic equation, I can calculate gradient vector. Every algebraic equation, if algebraic equation is x square plus y square, then its gradient vector is 2xi plus 2yj. Means small f, that is the potential function, small fxy equal to x square plus y square, then dfxy by dx is 2x, dfxy by dy is 2y, then gradient vector is dfxy by dxi plus dfxy by dyj, that is 2xi plus 2yj. If vector field capital F is vector field is gradient vector of any algebraic function in the world, any algebraic function, if it is possible that this is a vector field capital F is gradient vector of any algebraic function, then this vector field is path independent. Certainly vector field dot dr vector will be 0 from A to A or in a closed loop, guaranteed, if vector field happens to be gradient of any algebraic equation. Okay, can I prove that earth gravitational pull is, that is a force, right? Earth gravitational pull is a force, it's a vector field, is path independent. Can I prove it? Okay, now consider this is my earth. This is my earth. Okay, if this is my earth is round, but the way where I am sitting, that is flat. Person cannot see round earth, but it's possible. Can a person see round earth? I believe from aeroplane also you cannot see round earth. If it does not 8 kilometer high or something like that, 10 kilometer high, still you cannot see round earth. Then is it possible that from earth only someone can see earth is round? Is it possible? You need not go to space and then from 100 kilometer you see earth is round. From earth only is it possible to see the roundness of the earth? Is it possible? It's possible. From the Mount Everest, Sagarmatha. So from Mount Everest, the north of the Mount Everest is Tibetan plateau, and no one lives there. It is completely uninhabited, more or less. The way the area is still Mongolia or Siberia, more or less no one lives there. So no pollution is there. So from Mount Everest, that is, I believe, 9,848 meter high, around 10 kilometer high, 9,000 or 8,000, 8,848. So that is the height of the Mount Everest. From 9 kilometer height, if someone sees the north side, that is Tibetan side, he can see the curvature of the earth. He can see the roundness of the earth. Many people have proved it. It's possible that if you climb on the earth and from there, if you see north, it is so crystal clear. You can see hundreds and hundreds of kilometers from there. And there you can see the roundness of the earth. It is really round. Okay, so it's possible. Anyway, for that you need to climb Mount Everest and there should not be any cloud because at that height generally it will be cloudy. So at that moment you cannot see if you are lucky then. Anyway, so this is my earth and this is x-axis on the earth and this is y-axis on the earth. Consider like this. This is x-axis, this is y-axis. I could have considered this as z-axis, okay, or consider this as z-axis. Who stops here? So on this earth, this is x-axis, this is y-axis, and this is z-axis, x-axis, y-axis, and this is z-axis. Now earth is pulling everything along the z-axis. Okay, if you draw straight, it will drop on the plane, earth plane. Oops, I can try. Okay, so it fell direct. Okay, so if this is z direction, then earth is pulling in minus z direction. Understood, right? So what is the gravitational force through which the earth is pulling? That is gm. G is the gravitational acceleration. So gm, the mass on which it is applying the force. So acceleration into mass is force. So gm by r to the power 3. gm by r to the power 3 is the force with which earth is pulling. So as you go far from earth, the gravitational pull is decreasing heavily. So probably in 100 kilometer only you will be afloat. You cannot, you will not come to earth back. You will go to God's land. Okay, if you miss the earth, because earth is rotating, earth is kind of moving ahead at 100,000 kilometer, 100,000 kilometer per hour. Earth is moving ahead. First of all, it is rotating on its axis and then it is moving ahead with 100,000 kilometer per hour. If you go in space and you are not rotating around the earth, and if you miss 1 minute also, think how much then you are gone, because earth will not going, it is not coming, it will, it, when it will come back after 1 year, after 1 year it will come back to the same place. Okay, that is also not required. Earth will come back to same place after 1 year, not required, because earth is rotating around sun, and sun along with earth, mercury and so many planet, asteroid and this and that, sun is moving at even higher speed than earth. Earth is moving around sun, sun is moving around its galaxy, that is Milky Way, taking the earth and everyone, all family, full family, solar family, okay, full is moving around the Milky Way. Guarantee that you will go to God, buy ticket to the God if you miss it. Anyway, when you are studying in the earth, earth is taking you along with you. So, means you are making the, if you are studying the earth knowingly, unknowingly, you are moving in universe. Okay, the biggest example is if you see few stars that you know, okay, constellation, okay, constellation, I believe a big bear or something like that, or the seven saint saptarishi, it is called in India, or Sanskrit, or whatever, the seven star they are together, or the big bear or whatever it is. If you know a constellation, every year you watch it. So every January you watch it. Then every year, month wise, you will see. Anyway, if you see in January, in February, they will be shifted to west side. They will keep shifted to west side. Okay. But if you see year by year in the same month, then they will be in different direction. Okay, completely in different direction. Means they would have moved somewhere, but they should be at same location, right? Because earth comes back to same location. But this star constellation, if you see year by year in the month of January only, they will be in different place. This proves that earth is, sun is moving. So if you move anyway, now the force with which earth is pulling any item, earth is pulling any item is gm, gravitational acceleration into mass, by r to the power 3. But it is in a direction, right? If it is in a direction. If it is in minus z direction, it is in minus. So minus g is 9.8, that is acceleration. G into m divided by r to the power 3. Now, if it is in vector, then r to the power 3 will break now. R to the power 3, I'm sorry, it is by r square, not r to the power 3, I'm sorry. It is r square. If it is r square, and if I'm talking about the kind of its direction, then minus gm divided by r square and then unit vector. That is, or rather I say gm divided by r square minus k. Gm r square by gm divided by r square minus k, or minus gm divided by r to the power 3 r vector, because r is the radius of the, is a radial direction. If earth is round, then in the radial direction, that is your k vector. So if I say gm divided by r square and minus k vector, then minus k vector is the unit vector. So minus, I take it out, and r square I convert it to r to the power 3, and one r will go up, and the radial and k direction are same. It will transform into r vector. I believe this is some law is there. So minus gm divided by r to the power 3 r vector. This is the gravitational pull. If this is the gravitational pull, that is the vector field, then what is its potential function? If potential function's gradient vector is this gradient pull, then integrating it would, I should be able to get the potential function. So the potential vector, sorry, the vector field of the earth, force field, capital F is minus gm divided by r to the power 3 r vector. Okay, if I integrate r vector, okay, now I am trying to calculate, if it is r vector r to the power 3, now I am trying to find the potential function or line integral, whatever it is. What is the potential function for which the gradient vector is this vector, minus gm divided by r to the power 3 r vector? Let's integrate it with the line integral, dr vector. dr vector. Okay, so Now dr vector, now I have minus gm divided by r to the power 3 r vector dot dr vector. If that is the case, then dr vector and r vector direction is same. So r vector on top of it, I can take it out. So it will be now, if I take it out, then it will be minus gm by r square dr. Vector gone because dot product of r vector are same because we are calculating line integral along the radial one. If anything is falling, it is falling in minus z direction only. So dr vector, if I am calculating the line integral, that is in minus z direction. Here r vector is minus z direction, same direction. So dot product I can take it out. So now it is minus gm by r square dr. What is integration of r to the power minus 2? Then it is r to the power minus 1 divided by minus 1. So minus gone and now it is gm divided by r. That is the potential function. That is the potential function. Now I found one potential function. Okay. So if I find one potential function from the vector field, if I do some kind of integration, then now I prove that gradient of this vector field, gradient of this potential field, that is gm divided by r. Gm divided by r. Earlier we had vector field capital F as minus gm divided by r to the power 3 r vector. Now if I do line integral, it will generate one potential function. Now this potential function gradient, if I calculate gradient and it brings the force field directly, then gradient, the potential function is dependent only upon the force field, not on the dr vector, line vector. If that is the case, then it is line path independent. Now we have potential function as gm divided by r. Gm divided by r. Okay, if it is gm divided by r is nothing but the kind of r is any distance along the radius. That is, if I take in Cartesian coordinate, then it becomes x square plus y square plus z square square root. So the potential function is gm divided by square root of x square plus y square plus j square. If that is the case, if the small f is the potential function, so small f xyz, small f bracket xyz equal to gm divided by square root of x square plus y square plus z square. Now its gradient vector is dfxyz by dxi plus dfxyz by dyj plus dfxy by dfxyz by dzk. Let's go with the first derivative. Then derivative of 1 by square root of x square plus y square plus z square with dx will result into minus 2x divided by x square plus y square plus z square to the power 3 by 2. So net gradient vector will be minus xi divided by square root of x square plus y square plus z square to the power 3 by 2 plus minus yj divided by x square plus y square plus z square 3 by 2. Same thing for z also, plus minus zk. If that is the case, then denominator is same, right? Now it will become gm minus gm divided by x square plus y square plus z square to the power 3 by 2, and in bracket it will be xi plus yj plus zk. If xi plus yj plus zk is r vector, then isn't it the bottom is r to the power 3? So the force field, the force or gravitational force field was minus gm divided by r to the power 3 into r vector. Now gradient of vector field, gradient of potential function that we calculated through full line integral. Now that gradient came as same minus gm by square root minus gm into r vector divided by r to the power 3. This proves that this potential function is gradient of potential function is exactly same as force field. Then this potential function, what we are getting is dependent only upon the force field, not on the path. So it is path independent. If that is true, then Earth gravitational pull is path independent. If that is the case, then this potential function is also called potential energy. Potential energy function. Potential energy function means if it is path independent and if I am calculating the line integral, we are calculating the work done by the Earth. If that results in potential energy function, then if it is path independent, then potential energy, the change in potential energy is nothing but the work done. That's it. If it is path independent, it will dependent upon the two end point only. So if I drop an item from point A to point B, what is the work done by the Earth? See the power. See the power. See the power. How much power is in Earth's gravitational pull? Means Earth is a mother Earth, then how, with what force it made you stick with the Earth? Otherwise, where you will go? If you think in a spiritual way, then if you lose the Earth and you get disconnected from the Earth, what will happen to you? You will never be back on that. Not possible at all. It's not that 1 year you bake and wait and Earth will come to same location. It will never come. Okay, so stick anyway. So if it is point A and this is point B, then if I leave this item, then the work done by the Earth is point A to point B. Whatever the potential energy at this level, whatever the potential energy or potential function, if potential function is small f, fb minus fa, that is the work done. Okay, or if I if I if I if I leave this, from point, this is point A and this is point A and this is point B. If I leave this and it goes like this, what is the work done by the Earth? Same thing, because it depends upon point A and point B, and the point A and point B and your vector and your gravitational pull, not on the path independent. So either you point A to point B, you move through a circular line, you move a straight line, whatever it is. Work done is only dependent upon the two end point. That's why the Earth gravitational pull is path independent. We will take more examples, but we talk about a Stokes theorem. What we have learned is that if I have line integral in a closed loop, if I have a line integral in a closed loop, and if I divide, this is a closed loop. This is a closed loop. If I do the line integral of any vector field in a closed loop and divide by the area that this closed loop makes, then this is also divided by the area, then this is also called curling. If vector field is capital F and it is F1i plus F2j, then it is same as F2 dF2 by dx minus dF1 by dy. Or the line integral in a closed loop is same as the curl, if curl of the vector field dot d area vector, d area, that is dF2 by dx minus dF1 by dy, not vector. Whatever comes dxy, that is xy plane, in a solid surface. I am not saying solid 3D. In the surface, this circle is making a surface, right? The circle is making a surface. Okay, like this is a rectangle, this is a circular surface. So the line integral along this line, the line integral of if this is the vector field, somewhere under a vector field, this circle is there. The line integral of this vector field along this circle in a closed loop, point A to B, is same as curl of vector field F dxy plane. So df2 by dx minus df1 by dy into dA, that is dx dy, and then integration in a full surface. What is full surface? Double integration. X is minus a to a and y is minus a to a if it has radius a. So this is Green's theorem. So line integral in a closed loop of a vector field capital F is same as the surface integration, whatever surface it has, circular surface, surface integration of curl of F df2 by dx minus df1 by dy along the xy plane. Stokes says that not required that the circle, the area what it is covering, it is flat. Like this is a rectangular flat, this is a rectangle flat, and this rectangular right side what you are seeing, it is the boundary. So line integral in the boundary of this rectangle, make it small. So line integral of this flat surface along its boundary is same as whatever in a vector field capital F, whatever the curl of this vector field, that is df2 by dx minus df1 by dy, then integrating over the surface area, integrating over the xy plane. If this is xy plane, this item I kept on xy plane, dA, and then the integral over surface, that is if it is origin, then minus this point to this point, this point to this point. That is the line integral that Mr. Green is saying. Stokes is telling not necessarily that your surface will be flat. The surface can be like this. Can you see now? Surface can be like this. Surface can be like this. Now these are the like its boundary. Rather than you say a line curve, no, it is boundary. Can you see the boundary? It is like this. It is going like this because surface is not flat. Okay, if that is the case, if surface is not flat, that Mr. Stokes is saying, if surface is not flat, okay, then what would be then line integral along the boundary? Now boundary is not on the same plane. Then he is saying that vector field, okay, curl of the vector field, I believe I am right. So curl of, earlier it was curl of the vector field dA. Now curl of the vector field capital F dot dA vector. Curl of the vector field dot dA vector. Okay, now integrate over the surface. Now curl of the vector field, that is df2 by dx, in a vector field F. If capital F is the vector field, under this vector field, if I have a surface, now it is 3D surface. If it is like this, it is 3D surface, right? Now df at any df2 by dx minus df1 by dy, this would result in a vector. This would result in a vector. That vector dot dA vector. Now area has no algebraic equation. dA vector. Every moment this dA vector is different. Earlier it was in xy plane, and every moment this direction was same. So we did not. So this curl vector, curl of vector field F, if it is in xy plane, then it is in k direction. And area is also in k direction. We did not take it. But Stokes came into the picture and it's saying if your surface is like this and then your boundary is like this, the line integral along the boundary in a closed loop is curl of vector field F that will result in a vector dot dA vector. Now this area will is changing, right? So now it is a vector field. Area is a vector field rather than simply in one direction. So now area has come to vector field. So a dA vector multiplied by the curl vector, not curl vector of capital F integrated along the surface is the actual line integral. This is what Mr. Stokes is saying. And it is not necessarily that it will have continuous boundary. Boundary can be broken into more parts. Okay. How I can tell you? Like if I take a cylinder, this is my cylinder. Okay, so this is a torch, and consider this surface. It's a typical surface, right? Now it has two ends. This is one circular one boundary region, and another side there another boundary region. So it can have two boundary regions, two boundaries, not no problem. If that is the case, then this boundary line integral plus this boundary line integral, if you add both closed line integral, then it will be the curved vector field of the surface dot d area vector in a surface integral. That is the concept. So Green's theorem, I would say Green's theorem, it was 2D, now it is modified to 3D, and it is now has vector. So there Stokes theorem comes into the picture. Okay, so can we make it, can we do something that it will be have two boundaries, two circulations? Now I am going to make it as a cylinder. Okay, so it will be cylinder. Okay, I'll make it bigger. Now I am making it cylinder. Okay, it is cylinder. It should be visible. It is a cylinder. Now if I turn it into cylinder, now it has one boundary here and one boundary here. So surface can be molded in any fashion, and it can have more circulation boundary. Okay. Now if I just did like this, then it has only one continuous boundary. But if I convert it to cylinder, it has two continuous boundary. Whatever. Keep adding the line integral of the closed boundary, that will be equal to the vector field's curl of the vector field dot the surface area vector, the integration over the surface. This is Mr. Stokes theorem. We will prove it, and motor showcase that is pending, that will show. So we will proceed with more example, and we will prove it, the Stokes theorem, and then we will have really interesting time. So that we will see.